Hello everyone, today we're back on AtCoder. This is AtCoder Beginner Contest 328. There are more videos coming up soon, not just on the contest, but on other things, other very interesting things as well. So check out the channel, check out the previous videos, subscribe, and yes, always practice competitive programming. There are some frequently asked questions in the description. The link to the frequently asked questions will be in the description below. We'll try to solve as many problems as possible. Seeing that the scores here are lower, the problem should be easier, but let's not just predict that because sometimes it's the other way around. So yeah, the contest is starting in a couple of seconds. Let's go. Let's open up the first 4 problems. So there's programming with n problems. The score is SI. Print the total score of all problems with a score of X or less. So I use the competitive companion and the CPH Judge extension. So we just read n and x. We have some if s is smaller or equal, then the sum is print. This is the print all problems with the score of the sum of that's A. AtCoder Kingdom uses a calendar whose year is n months, as d by days, and day I of month I. Day 1 of month I to di of month. From day 1 to day d. How many days in a year have rep digits dates? Wait, what? Rep digits? What are rep digits? Day here, day j of month I is said to have rep digit date if and only if all digits in the decimal notation of I and j are the same. So you can just iterate over all of them. So can I just iterate over so from day 1 of month I to day di of month yes, so we just reset from the okay. It is not a cumulative, so we can just go over and we have to check if I and j have the same old digits. So we can just convert si to string sj to string. We can just build a set of these characters for each element in si. We're going to insert in the set for each element in sj, and then count will be if the set dot size is equal to 1. You're given a string s from s1, so lowercase English letters initially. QQueries of the form is represented by L and R in the substring from SLI to R, which ranges how many places are there where the lowercase English letter occurs twice in a row. In other words, the queries are a lot and the n is a lot. So what you can do is you can pre-compute at what places do we have this happening. So let's say that this is like that. So let's say that if s of I is equal to s of I plus 1, then a of I is 1, happening at that place. Then we can use prefix sums to compute so we can use prefix sums and say that prefix if I is 0, prefix of I is AI, else prefix of I is prefix of I minus 1 plus AI. Then for each query we are given L and R. And then we want to say that so from inclusive from L to R minus 1, because if I'm getting to R that means that so prefix at R minus 1 minus if L is 0 then 0, or prefix at L minus 1 is our answer as far as I think this passes. Okay, problem D. You're given a string S consisting of 3 different letters. As long as S contains the string ABC as a consecutive substring, repeat the following operation. Remove the leftmost occurrence of the string ABC. Print the final string after performing the above procedure. As soon as we find the leftmost occurrence, we just remove it and then remove it back, and then do this all the time, because the leftmost occurrence will always be so there's string answer so if answer dot size is smaller than 3, answer closure tag s of I, continue. Else we check if answer substring from position n minus 3, n minus 4, the last n minus 1 is that, n minus 3, right, from n minus 3, if that is, then we pop back 3 times the answer. So while, I mean not while, as long as we have this, we pop back that, or no, or we need to, we pop back that, and then we say, wait, my brain blocked. I'm gonna add some ladder at the end. So like this, I add this ladder and then I pop back. Okay, gets accepted. Now we need, okay. We're given a weighted, simple, connected, undirected graph where vertices are numbered and edges are numbered. Additionally, a positive k integer k is given. Edge I connects vertices u and I with weight. For a spanning tree T of the graph, the cost of T is defined as the sum modulo k of the weights of the edges T. Find the minimum cost of a spanning tree in the graph. Because there's a little of these edges, how many, there's small amount of nodes. So for, there are 8 times 8 times 7 divided by 2 to the 28 is a lot. So there's no way of doing this. But wait, for a spanning tree T of the graph, the cost of T is defined as the sum modulo k of the weights in edge. But the sum modulo k is the same as saying that we first modulo k everything and then we do this. Isn't that the same? Or no, maybe not. Maybe not. But for each node, we can pick one of these edges, right? As long as as long as they're connected. But I don't understand, isn't... Yeah, because K is actually doing... Like, I thought that finding the minimum... But essentially probably not, right? Okay, E. I mean, yeah, so it's probably some brute force, so 2 to the n is very small. But for each n, but there's not 2 to the n, there's actually 2 to the m. Yes. This choose this. There's very small, there's only 1 million of these combinations. So, okay. How do we iterate over all of the there's the Gosper trick that we can use. Can we use the Gosper trick? I think we can, right? Yes, we can. Gosper hack. I don't have it here. Let me just Gosper hack. I think we can use this. Okay, so the Gosper hack essentially does a bit masking of combinatorics, like brute forces every combinatorics in a bit mask. So, okay, what we can do, it fits in an integer, so I don't need a long here. I can fit in an integer. But let's keep it simple. Let's keep long because I don't know this shift here. Will it overflow? So I need the edges to be in an array. Not doubly. And then I can do a Gosper hack on n times n minus 1 divided by 2. n minus 1. Now we have to quickly sum up the edges that are in the mask. But we also have to check is it about 3. We have to check is it a valid tree. So let's have a DSU. If DSU.components equal 1, answer is answer in the sum. And case long. Right, case long edges here should be long. Alright, that passes. You're given Q triples A, B, D. Okay. A subset S. Gets accepted. A subset S is defined to be a good set if there exists an integer sequence of length n that satisfies that the difference between this is that. Okay. So we have some constraints, and then starting with S as an empty set, perform the following operation. If S union I is a good set, then add I. So we're starting with some set. We want to say that starting with S as an empty set. So we go through the first operation. We say, okay, if is defined as if union I is there exists an integer sequence of length n. That this is d. This reminds me of one particular DSU. So let's fix the AI element. The BI we know already what should it be. So we know already what these two elements are. Then for the second query, so do we do it just basically brute, like simulate this? I would think so, right? Because there's no optimality here, we just simulate it. AB and then a difference. X at A is going to be 0. But yeah. This is a Q. This is a. So if we do this, then yeah, this is a DSU. So yeah. Okay. There's this constraint DSU that I know that already exists. Constraint DSU. Data structures. There's a DSU that is shows library GitHub. There's some. I know that there's some. I know that there's some augmented DSU. Yeah, used for maintaining system of form effect equations along with their queries dynamically. I know that this already exists. Okay, so there's the thing. Here's the merge. Here's the merge. The number of inconsistencies. So in the merge, what we do is we find if is a flaw. Instead of reporting a flaw, we're gonna return false. Here, return true. And then go okay. And then if it's okay, I will. But this is A minus B is D. Oh, this is different. We need we need to maintain it differently. But it's the same idea with the DSU. So number of variables, number of variables. We say that yeah. So yeah, okay. I mean, yeah, this works, right? Like a minus x minus a minus b equals d. Find a, find b. Potential at a, b. Yes. So I think that that's okay. So if it's okay, then I print I. This is if okay, no? Yes. Okay. I'll try to understand it later, how this works. You're given two sequences, A and B. Oh, we're at the last problem. We have 1 hour. We're two given sequences, A and B. You can perform the following two types of operations on the sequence A any number of times, in any order. Split A at... So I'll see if that passes, but that should pass. Oh, wrong answer. There are only two wrong answers. Let's see. This is the maximum case, probably, where I overfill something. Still, I should have added plus something. Plus 10, you always add some. I still wrong answer. Okay. This is 10 to the 5, right? This is 10 to the 5. Oh, of course, overflows. Um, 10 minutes penalty because of nothing, but now it shouldn't overflow. No, that's exactly. You're given two sequences like this, so you can do following number of operational sequence A any number of times. Split A at any position, freely rearrange the split sequences. Each split incurs a cost of C, more formally a cost of x minus 1 times C. Take a sequence x minus 1. Take a sequence of length x plus 1. And a permutation P. More formally, at the cost of x minus 1 times C, take a sequence of length x plus 1 and a permutation P of length x. Replace A with the concatenation Choose an integer k and any element of A at k to the value of the chosen outcome. Oh, there are a small number of these elements. Okay, there's a small number of elements. The cost could be huge. So I need to understand an example what they want. For example, you can make A and B equal by performing the following operations. Add 2 to A2. So the addition here, wait, choose an integer k and any element of A, add k to the chosen element of a cost k, of a cost offset element k. So the idea here is that I can make any element. I need to rearrange them somehow. They're like really close to B, and then add this thing here, this k. So the additions, I can perform them at a later step. I first need to perform the splits. So split A into 3, 3 and 7 to 5. 3, 3 and 7 to 5 and swap their order. It costs 1 and A becomes, it costs 1. Each split here costs 1. So we can split and swap their order. Splitting. I wonder if I split it like this, there's cost is 2. So C is 1, let's say, then this cost is 2. But what if I split it like this first, rearrange that sequence there. There's 2 million ways of choosing whether I split at that point or not. For each of these way, I choose whether or not I split at that point. I have to optimally say what is the order that this occurs in. Okay, so we know that. So the complexity we want is 2 to the 21 times n. So 2 to the n minus 1 times n is the complexity we want. So how to achieve the optimal order given some splits that we're going to take? How to achieve the optimal order? Because there's essentially in brute force scenario there's 2 to the n minus 1, but then for each of this it's like n factorial. There's n factorial things I can do, but I can rearrange, but there's an optimal, probably a greedy way of doing stuff. And how is this possible? Let me just see the standings. Yeah, that's bad. How am I 200th place? Does that incur that penalties probably? Ugh. So splitting that. Okay, so let's say that we have some splits, right? how do we arrange them optimally? It's not particularly easy, is it? Maybe the splits are very, like, maybe divide them into groups, like, in case the splits are small, the number of splits is small, we do one thing, like brute force. If the number of splits is high, do something clever. But I don't see why we want to split it like this. And there's 22 factorial, it's a huge number as well. So. So what we do is for each of this window in the first here, we want to somehow correlate it to the cost. So what we can correlate is having some LR, the cost to get to B LB RB. So given some interval and given two intervals, what is the cost? And we can brute force this for all intervals here and for all intervals here. We can calculate their cost. And then now, given the splits, we have some intervals. What is the most optimal cost to arrange them somehow into... There's still a lot of permutations. We need something clever here. Okay, so let's pre-compute this dp. So we say dp int lb is p, int lrb is p plus size. Is that correct? One. So imagine this one. This is 1 minus here. Size is 2. From dp at l a r a lb rb plus equals. So what is this? Why this doesn't work? There's 4 vectors here. There's so okay. So this is the absolute value between a of LA plus K and minus B of LB plus K. So DP is essentially saying if I move this interval to there, what will be our cost? Now, I don't need actually this quadratic DP. I need just this, and one more function because LB is already null. LB is already null. Okay. But still, okay, we have all of these brute force. Still we need, okay, we split them up somehow. And how do we correlate them? There's 1 million. So starting from a point, let's see what Wolfram Alpha gives us at No, we need to exclude. Is it so isn't this like a DP problem? Like given some intervals, given these costs, if I put an interval here, AI, what is my DP here without this interval? So I can sort all AI intervals, and I can say yes. So we just do like another DP. Okay, so first we need to split the intervals. We need to get all of these intervals. And the easiest way to do this is so there's n minus 1 points that were split. So we go over all of this. And if I and S, we split it to the last element and I plus 1. No, I, just I. Yes, so just I. The last element in the last is 0. So we split here and we say that intervals dot pushback last and I. Last is now I plus 1. So we do this. The intervals are like that, okay. So we have some intervals. Then we have these intervals. Then we need a DP. Then we need a DP, and this would be like a quadratic DP. Saying that, okay, how many intervals? So let's say that this interval that size. And how many points we have and what interval we are. There's n points and there's this many intervals, and here we want to minimize something. So let's say infinity, and let's say that infinity is this. Okay. Then for each just DP. For each point, we will try each interval backwards. And we'll say, okay, how much is the cost here? So So LR intervals. No, we need interval. Size of the interval is this. This is the size of the interval. And then what we want is saying, okay, so if what we want is get dp, so this get dp is I minus the size of the interval if get dp, so previous dp is get dp is smaller than 0, then that's cost of zero. But if I have to add an wait, so I'm here currently. I add some interval. Wait, this is ordinary dp. What am I doing? I add some interval. This is our previous cost. No, I know this problem. I have seen it somewhere else. Let me just. I'm pretty sure I have seen this problem somewhere else. Because we can rearrange the intervals however we want. But there's some invariant here. Some invariant of this rearrangement. No, 3 to the wait, there's some intervals and then 3 to the 22 is a lot, right? 3 to the 21 is also a lot as far as I know. So I'm thinking all these intervals, but then I'm thinking like a DP with mask for each of these, and I know which interval have I put in there. That works, but it's a lot. It's the dip is too much to handle. It's 3 to the n, but 3 to the n doesn't work. There's one problem here. Was it this one? But it's not. It's not. I thought that this is the same problem. Wait. So rearranging. So okay, we can solve it 3 to the n minus 1, but that does not. Okay, so we have these intervals. We just have to do a deeping here. So we know this DP, we know this DP, but I think it's too slow. This is too slow. arrangement. Optimal. I'm pretty sure we can do this. What am I missing here? It has to be simple, so dynamic programming interval schedule. The weighted interval schedule. Weighted interval scheduling is totally I don't no, it's not weighted interval scheduling, it's maybe not that slow, but I think it is. It's 3 to the it's 3 to the n, but 3 to the n will fail. I'm pretty sure I'll fail. Daily. It's too much. Doing 3 to the 21 is a lot. Mute interval. Like this is like an exact cover, but maybe there's a way how do we split it. Maybe there's a way just to Maybe there's a way to, if here is a split, the last split with some known intervals. But then that's impossible. For each of these splits we can do it, but we have to do it very fast. What if I say this, the thing I said in the beginning? Like arrange the first j interval somehow here to this point. So to this point it says, okay, what is my cost if I have already arranged the first j intervals with up to this point I, right? So if I want to arrange this other interval, I can put it anywhere here that fits somehow. Could this be the cubic DP problem? How did this cubic DP problem work? In each position, yes, this was okay. So we have, in this position we had the first interval, or in this position we had the first. Then we merged from this position to this position. Is it possible to add this interval here, jth interval here, with just rearranging some intervals here and some intervals here? Okay, look up the AtCoder DP contest if there was some similar solution, some similar problem to this. There is this intervals problem, but this was something else. Grouping problem. No. Permutation problem. I know this one. Power problem. No. Weight problem. Some of these problems maybe. Something similar. Right, so I think there was this problem. Like the DPI and DPJ. So the first J intervals we rearrange it up to the ith point. Is there a way to rearrange them up to the ith point? No, I want to read the tutorial. It's just a DP, right? It's just DP. I don't see it. If n would have run to 19, let's say, it would have been possible. There's no, but there's Japanese editorial. There's no need to perform the second operation multiple times. The second operation after going only once is good to do the second. No, the first operation here multiple times. Second, the sequence of if we decide to begin, we consider following DP. Minimum cost determining the terminal conversation triggers by the term. Minimum where P is a permutation. C times the number of dating each block in the second operation. I can't understand the translation is very bad. The number of transitions for the certain length cases performing. There's 2 to the n times n. Let me just understand this. So there's dp, there's this dp, and then pop count. Who writes code like this? Cost is C. So there's some interval L and R here, and in this S we take away something from L. We add something from R and take away something from L. Some permutation. Oh, we take away everything. Aha, this is. Wait, no. I have no idea what this is, but we take away some permutation. It's a completely different solution than what I had in mind. But probably this is why, because This is why it works, because you have disconnected with you have it in one solution instead of in two. Yes, okay. This good set query, I think I kind of understand what the data structure is, but it's essentially like a DSU with you can look it up, but essentially it has some propagation, because this when you find the root, you propagate something back to the parents. I mean, and because this is commutative and associative, the sum it's fine. I mean, not the sum. The yes, it's kind of the sum of these. But okay, I mean, I don't know. I had a totally different idea for G, which apparently doesn't work. Tell me in the comments if you can get it to work. If my idea could be, but I don't think my idea is a little bit too slow. 3 to the n times n. So let me go through all of the problems and explain them really quickly. So problem A was just simply summing up integers that are smaller or greater or smaller or equal to x, and we just want to print the sum. Pretty straightforward. Problem B was iterating over some months and then some days in the month, and then we wanted to check if all of the digits and here matched and how many of these actually happened. So there's of course a better solution than this, but what I did is I just converted them to strings, both the month and the day, and then I had a set of characters, and in that set of characters put each of these strings here, character by character, and I counted only if the set had size 1, which means that only one character appeared everywhere. That's B. C, we were given some string and queries, and for each query we wanted to ask from this position to some position here, how many times, if I get this substring, how many times in this substring there are 2 consecutive characters. And what you do is, like, for each 2 consecutive character, if there are 2 consecutive characters, I put another array A to 1, and then I have prefix sums in this array, so I can query it very fast, because prefix sums because this is commutative, so and associative, right? So you just don't care. You sum them up, all of these A's here, that the events that happen, and then for each query there is an interval from L to R minus 1, because R, we cannot have R, because in position R there could be one that is position R plus 1, and this is R plus 1 is not in our string, so we go one place back, and if we want to sum up how many of these A's occur in that interval, we just do prefix sum from R minus 1, which is included, minus prefix sum of L minus 1, but this could not make, if L is 0, then this should be 0 as well, because there's no, this will go out of bounds, and it's super straightforward problem. Problem D, we take the first occurrence of that ABC and we always delete it, and we shift this whole string like that. So this is a well-known problem, and just what you do is just you add character by character, and as long as there's the string is bigger than 3 and the last 3 characters are ABC, we delete the last 3 characters, and we repeat deleting these last 3 characters, and we repeat adding a character as well. That's straightforward. Okay, so MST here is the only problem that it kind of, I mean, not the only problem that requires thinking, but the only problem that this is a brute force problem and required observation that the combination between the amount of the amount of not minimum spanning trees, but the amount of, like, if I choose from all of the edges, I choose n minus 1 of them. So this is this is like m choose n minus 1. So that should work as well. So m choose n minus 1. Then the mask. Here it gives you, each time this function is called, this Gosper hack function calls back a function for each of the masks. So it's just you brute force through each of the possible n minus 1 configuration of like taking subgraphs. So we have some graph, and we say we will take each subgraph that has n minus 1 edges, and this Gosper hacks does it extremely quickly. I mean, we just linearly go through each possible graph, but there are a lot of graphs, and there's exactly m choose n minus 1 graphs, but it fits in the time constraints. I have a DSU which checks if this then we have one component. It means that it's a tree at the end, and the sum, we sum up all of the weights that are chosen, all the weights of all of the edges that are chosen, and then we minimize the sum. This is the only problem that is kind of interesting, because is the Gosper hack. This here good set query is a well-known problem. We talked about it, and so you just sum up you just have like a DSU, and then when you find something, you sum up the potentials at along this path of the DSU. And then you want to check always that the potential is that essentially if it's not D, if they're both in the same set, and the potential between them, so on the path between A and B is not D, then this query doesn't fit. But if they're in a different set, what you do is, like, you have the potential of this parent is of this RA parent is D plus the potential of B minus. You will need to draw that, but it's just summing up. It's just because you will be putting this tree. You will be attaching this tree to the RB here. You have to also calculate the potential now at RA according to this, right? So this is kind of an interesting problem, and yeah, it's a known problem. It's a known problem. G, we talked about it. I had a different solution. I now see what they do. I understand what they do, and essentially it's just incredibly simple. You want to cover. You want for each of these BIs to have like a mask, and then when you put some interval here, when you split something in AI, you you can put it here. Let's say you get some interval from AI. You can put it here, you can put it here, you can put it here, or you can put it here. And for each of, like, if I put it here, I want the DP is that, like, I cover this interval, and what else is not covered. Let me see what else is not covered, but I cover this interval, and I cover intervals and intervals and intervals all the time, but they cannot overlap. This is the idea. When you cover some interval, they cannot overlap. Uh, kind of simple problem, I would say. I can probably code it right now, knowing the solution. But yes, I want to upload the video as soon as possible. So yes, I don't really have time. Yes, we will upsolve all some problems later. Thank you guys so much for watching, and I see you in the next one.